Hey guys, from this video we're gonna move on to Riemann integral, and in this video I'm gonna introduce you guys some very simple and basic concepts for the preparation for the definition of a Riemann integral. And I believe actually we have already get exposed to integral in high school, and remember how we did what we did to like understand what the integral is. What the integral is to kind of like calculate the area of the shape of the which is constituted by the function, the curve, and the axis, right? And it's pretty much the same geometric meaning of the Riemann integral, except we also introduce limit into the formal definition of the Riemann integral. So in this video, I'm gonna first introduce the concept of a partition. So a partition P of a interval AB is a finite and ordered set P. So it's like what we did to first divide the interval into several, actually a lot of small subsets, right? And actually the more subsets you divide it into, then the more accurate your approximation will be, right? Because we don't, it's the area is not like those like triangle or rectangle. We don't have a formal formula to calculate the area, so we kind of like do a approximation. We cut the intervals into several a lot of pieces, and for each piece we use the formula for the rectangle, right? To approximate and add them together to take the sum of all the rectangles and then approximate this to be the integral of a function. So it's the same when we take partition, but you have to remember P is a finite and ordered set, and x0 and xn are the endpoints A and B. And for each subinterval, we also have mk and capital MK, which are the infimum and supremum of the function in that interval. Right? How are we going to use them? We're going to also introduce the lower sum and the upper sum of the function f with respect to p. And it's defined as take the sum of the sum of the area of those small rectangles, right? But the difference is the height. The lower sum, for the lower sum, the height is the infimum of the function at each interval, and for upper sum, it will be the supremum of the function at each interval. And you can imagine actually where the lower sum and upper sum you have to pay attention is that it's the lower sum and upper sum of f is kind of related to how you partition it. It's the lower sum and upper sum of f is related to the partition, and different partition can obviously give you different lower sum and upper sum, right? So you can imagine the real area of that shape will be between the upper sum and lower sum, right? Because for lower sum, you always take the infimum of you always take the height as the infimum, and you always take the height as the supremum for the upper sum. Okay, another concept is the refinement. As I said before, the lower and upper sum is related to how you partition it. So a partition Q is called a refinement of a partition P if Q contains all the points of P. Or you can imagine it as a Q is like partition the original interval AB further, right? And since it's partition it further, it will definitely get a better answer, right? Because you actually divide it into more subsets, right? And we sometimes write P belongs to Q to show that Q is a refinement of P. And we have two small lemmas, which are, I think, quite straightforward. So if P belongs to Q, if Q is a refinement of P, then the lower sum of F with respect to P is smaller than or equal to the lower sum of F with respect to Q, right? Because we know that the accuracy of Q the approximation of Q will be like better than the approximation of P, right? So, or it's like suppose we have x1, x2 here, and we know that and assume that x1 and x2 belongs to P, and they also belong to Q, right? Because Q is a refinement, and since Q is a refinement, Q might have also like Z1 here or Z0 between x1 and x2. So if we change it like to see the difference more obvious. So when you calculate the lower sum of Fp between x1 and xq, you will get the area of this rectangle, right? But when you calculate the area for Q, you will then get these two small rectangles. And it's quite easy to see that the area of Q, the area of those two small rectangles will be larger than the previous one, the area of when you take only the partition of P, right? So it's easy to say that the lower sum of F with respect to P will be smaller. And similarly, the upper sum of F with respect to P will be larger, right? Because for the refinement, you have more like subintervals. And it's the same. Originally, you take the area of the rectangle like this one, this green rectangle, and for partition Q, you will take only this part and this part. So the purple rectangle, the area of the purple two small rectangles will be smaller than the green rectangle, right? So the upper bound of F with respect to P will be larger. And you can actually, I think from this lemma and the definition of lower and upper sum, we can almost guess what is the definition of Riemann integral, or when we can say that the lower and upper sum are very extremely close to the real integral, when the lower sum and upper sum are so close that they're almost close together. They almost get together to one point or one value at each subinterval, right? But we're gonna give a more rigorous definition in the next video. And the second lemma is still quite straightforward. If you are given two partitions P1 and P2 on an interval AB, then you will have the lower sum of f with respect to p smaller or equal to the upper sum of f with respect to p2. Well, now p1 and p2 are two arbitrary intervals, and you don't know which one is like the refinement of which one, or they might not be each other's refinement at all. But what you always need to remember is that no matter what PQ are, no matter how you choose the partition, the lower sum will always be smaller than the upper sum, right? I think this is quite straightforward because when you take lower sum, you always take the infimum one, and when you take the upper sum, you always take the supermum, and supermum will be larger or equal to the infimum in a small in every small subinterval, right? But you might well say that, well, since PQ are arbitrary, two arbitrary partitions, it's possible that their subintervals doesn't correspond with each other, right? But even though we can still prove that this lemma is true by taking a refinement of P1 union P2, right? And now using the lemma 1, you will have the lower sum of f with respect to P1 will be smaller than the lower bound of f with respect to q, right? Because q is a refinement of P1, also P2. And for q, its lower sum will smaller or equal to its upper sum, right? And then use this part. The upper sum of q will be smaller than the upper sum of f with respect to P2. Then we get the lower sum of f with respect to P1 will be smaller or equal to the upper sum of f with respect to P2. So they're quite straightforward, huh? And this is what I want to talk about in this video. So it's kind of like a preparation for the definition of Riemann integral. And further, in next video we will see the rigorous definition for Riemann integral, and we will also see some theorems and lemmas and some interesting properties of these lower and upper sums, and also the integral itself.